Hello everyone, this is Dr. Young. In this video, right, we're going to finally practice all of those things that we learned in the previous videos, right? We're going to try to put it all together. So remember that the number of signals, right, we said that that was, that equaled the number of environments, right? The number of hydrogen environments. The integrations, right, that gave us the ratio of hydrogens in each environment. The splitting patterns, right, that equaled the number of neighbors plus one. And then the chemical shift, right, tells us what is attached nearby. So we're going to put all of these together to try to take NMR spectra and predict what we think that the structures should look like. So let's take a look at this first one. We're going to pick a small molecule, relatively simple, so we can figure out how does this NMR confirm the structure of this molecule. So what I'd like you to do is just take a minute here, right? I have the formula for you. I didn't give you a full IR, but I gave you an important peak from the IR. You should be able to look at this, 3,200-ish, and think, well, that's above 3,000, so that's probably an OH. It's a little on the low end for an OH, but it's probably an OH. So my molecule has an OH in it, and it's C3H8O. And there's really only two possible products for this. So why don't you take a sec, draw those two products, and see if you can decide based on this spectrum which of those two products it is. Right, so if you take a look at this, so I've got C3H8O. I can really only make two different alcohols here. I can either make the isopropyl alcohol or the 2-propanol, or I can make 1-propanol. Those are the only two options I can make. I have no degrees of unsaturation, so I know there's no double bonds or rings. And really the only two ways I can assemble 3 carbons, 8 hydrogens, and 2 oxygens are these two ways. Now I just need to decide, go look at my spectrum and say, well, which one of these is supported by this spectrum? So I'm going to take a look at the first one here, right? And say, okay, for the isopropyl alcohol, I'd expect to have 1 peak for the hydrogen and oxygen, 1 peak for that, and then 1 peak for these, right? So altogether, I'd expect to see 3 signals. And in fact, I do, right? I see 1, 2, 3 signals, a 1H, a 1H, and a 6H. That sounds pretty good. If I take a look at the other alcohol, I'd expect 1 for the H, I'd expect another one for that CH2, a different one for that CH2, and a different one for that CH2. So that's 4 signals. That's 4 environments. I expect to see 4 signals. I don't see 4 signals. So already, right off the bat, I think that the one on the left is correct and the one on the right is wrong, right? So even just looking at the number of signals. But let's dig a little bit deeper and really, really convince ourselves, right? If I take a closer look at this, for the OH up here, the one I circled in red, I'd expect that to be a 1H peak, right? There's only 1 hydrogen in that environment. For the blue one, I expect that also to be a 1H peak. And then for the green one, I expect for that to be a 6H peak. And that's exactly what I see, right? I see a 6H peak, and I see a 1H peak, and another 1H peak down here. Now, I'm not too sure which one's which at this point, but I do see those 1H peaks. So even the integrals match with the idea that this could be the 2-propanol, the isopropanol. If we dig deeper yet and look at, well, what do we expect the splittings to be? My 1H peak, it's an alcohol, and when they're dilute, they tend to be just kind of broad singlets. They tend to be just broad singlets. Now, they can sharpen up, but they tend to be broad. But they tend to just be singlets because they're not coupling with things. If I take a look at my blue one here, this 1H, it has 3 neighbors to the left and 3 neighbors to the right, right? Because it's got a methyl here and a methyl here. It's got 6 neighbors altogether. So I'd expect for that to be, right, I would expect that to be a 1, 2, 3, 4, 5, 6, 7. I'd expect that to be a septet, which to me looks kind of like this friend right here. That looks like a septet to me, which means then, therefore, this singlet here must be that 1H. And then just to confirm, the 6H, the one I've circled in green here, they only have 1 neighbor, namely that blue one. So that should be a doublet, and sure enough, that is what I see for the 6H peak. It is a doublet, right? So I do see that the blue is a septet. I see that the red is a singlet, and I see that the blue one, or sorry, the green one here is a doublet. So all the splittings make sense also. Lastly, just to double check with the actual chemical shift here, right? The red one, alcohols can be like anywhere from like 10 to 1 ppm, depending on if they're attached to aromatic rings or if they're just attached to sp3 carbons, whatever. The blue one, this is attached to something electronegative, so I expect this to be somewhere between 3 to 4.5 ppms, which I do, right? It's right here at about 4 if I take a look, right? It's slightly above 4 point something. And then I would expect my green one, right? It's just alkane-like. It's going to be between 0 and 1.5, probably on the higher end because it's near an oxygen, even though it's not directly attached to one. And sure enough, that's what we see here, right? It's somewhere between 0 and 1.5. It's on the higher end of that because there's an oxygen nearby. And so everything about this makes sense that that's isopropyl alcohol. So that's how we can use this information to help us decide, yeah, that's the molecule that I think I made. Now, if I take a look at this one, same formula, same IR, right? So I know there's an alcohol. This is the same thing. It's either going to be, right, the isopropyl alcohol or the 1-propanol. And like we said in the previous slide, right, that we had 1, 2, 3, 4 peaks here. And now we see our 1, 2, 3, 4 signals. So that all jives. The red one, right, should be a 1H singlet. And it should show up, again, somewhere between 10 and 1 ppm. So that's got to be this one. That's got to be this one. It's the only one that's a 1H. And it's a singlet. If I take a look at the blue one, right, I expect a 2H signal from here. It's only got 2 neighbors, the green one, so I expect a triplet, and I expect that to show up between, again, 3 to 4.5 ppm. So that must be the 2H triplet showing up between 3 and 5 ppm. The green, another 2H, but now it's got 3 neighbors to the left and 2 neighbors to the right, so I'd expect to see a sextet. And it should be pretty alkane-like, somewhere between 0 and 1.5. It's not directly attached to the O, but it should be kind of on the down field part, the more deshielded part. So that's almost certainly this one, right? The complicated pattern, 1, 2, 3, 4, 5, 6. And then lastly, right, the 3H all the way to the right, better match here. This should be a 3H peak. It should be a triplet because it only has 2 neighbors, and again, between 0 and 1.5 ppm. So these all match up too, right? This NMR confirms that structure. How about this one? So here's a new one, new formula, new IR data. Again, you should look at your IR data, and if you don't remember, right, 1759 almost certainly is a carbonyl. Almost certainly is a carbonyl. It's got to be a carbonyl. I remember alkenes are a little bit further down, more like 16 or 1500 or so. If I look at my formula up here, I see that I have 1 degree of unsaturation, right? Because I'm missing a couple hydrogens there. So I've got one either ring or double bond. I know it's a double bond because I know there's a carbonyl here, right? There's no ring. Only 1 degree of unsaturation. Here it is. And so now I'm going to take a look at, right? There's a few things this could be, but I'm going to take a look at my NMR and kind of make some pieces here, right? So let's first start with this piece, this 2H peak right here. This is saying this is a 2H peak. So I'm going to draw 2 hydrogens here, right? Because it says it's 2H. Now it also has this is a quartet, and that means that I have 3 neighbors. So next to it, I'm going to draw 3 neighbors. Draw 3 neighbors, right? That quartet means that there's 3 neighbors. So 3 neighbors. I also want to take a look at the fact that it looks like it's at about, 4.1-ish or so, which tells me that it's attached to something electronegative, right? This is a hydrogen on a carbon that's attached to, remember I was saying some sort of halogen or oxygen or nitrogen or something like that. In our case, this must be oxygen because that's all I've got in my formula. It must be attached to an oxygen. That must be the electronegative thing that it's attached to. So I'm going to put an oxygen here, right? That's why it's shifted down to 4.1. That's why it's downfield at 4.1. So just from this signal here, this 2H quartet at 4.1-ish, I'm able to build this chunk. It's an ethyl piece attached to an oxygen. I got all that information from there. I'm going to continue to this 3H peak. So I know this is a 3H. So I've got, I'm going to draw the 3 hydrogens on 1 carbon. They're all in the same environment. And now if I look next to it, right, this is a singlet. right? Which means it does not have any neighbors. Whatever is here, it does not have any neighbors. So the question is, what might it be attached to? Since this is showing up at, again, like 2.1-ish, that means we're talking about hydrogens on a carbon, and that carbon is double bonded to something, either a C or an O, right? Remember we said these are one away from an alkene or a carbonyl. In my case, I've already decided that I have a carbonyl in my molecule, right? Because I see in the IR 1759, that tells me that I have a carbonyl. So that tells me then what that double bond is to. It tells me it's to an O. So it must be that this CH3 is attached to the carbonyl, the C-double-bond-O. Again, why? Because it has no neighbors. So putting a carbonyl here means that there's no neighbors. And because it shows up at 2.1, right, that's the range where we see hydrogens on carbons that are next to double bonds. So it must be the thing attached to the double bond. Let's move to the last one, this 3H peak right here, right? Again, so it's a 3H peak. So I'm going to draw another CH3. What is it attached to? Well, this is a triplet. That means that the number of neighbors is 2, so it has 2 neighbors. That's easy. I'll just draw 2 neighbors. Only one way to do that. And then I don't know what else is attached beyond that. This is in that 0 to 1.5 range, which means it's just alkane-like. There's nothing too special going on. So I'm just going to leave it like that. There's nothing too special going on. So from each of these peaks, I was able to get this information. Now, if I take a look at this, right, I only have 4 carbons in my molecule, and yet I have drawn 1, 2, 3, 4, 5, 6 carbons. So clearly, some of these pieces are overlapping with one another. And if I take a closer look, I think it's these two. I think it's the ethyl piece right here and right here. So now I'm just going to put these 3 puzzle pieces together so that they make sense. I know that oxygen is attached to something. I know that carbonyl is attached to something. So I think that I have the carbonyl attached to this CH3, right, which came from this piece up here. And then I think it's got to be attached to this O. Those are the only 2 end pieces. It's got to be attached to that O. So I'm going to draw an O on the other side of this carbonyl. And then we said that that O was attached to the CH2, and then that CH2 was attached to the CH3. So this must be the molecule. I must have ethyl acetate or ethyl ethanoate. I must have this molecule, right? Where the green is talking about this, the red one's talking about this, and the blue one's talking about that. And so using the information in the NMR, I'm able to deduce this structure. That must be my structure, with the help, again, of the IR. One last example here. So let's have a little bigger molecule, right? So C9H12O. If I look at the degrees of unsaturation for this, I would calculate that there's 4 degrees of unsaturation, or double bond equivalence. If I look at the IR here, I see that there are CC double bonds, maybe even aromatic ring. That's kind of low for CC double bonds. It could be an aromatic ring, but definitely CC double bonds, not an OH, not a carbonyl, not a triple bond. And then I have my NMR, right? It looks like I have 1, 2, 3, 4, 5 different environments. I've got some integrations. I see my integrations are 1, 1, 1.5, 1, and 1.5. So right off the bat, I know that I can't have 1.5 hydrogens. So I'm going to multiply these all up by 2 to get whole numbers, right? So I'm going to multiply everything by 2 here. So I think that this is actually a 2H peak. I think that's a 2H peak. I think this is a 3H peak. I think that's a 2H peak, and lastly, a 3H peak, right? So I'm multiplying all the integrals up. Remember that the integrals are just a ratio spat out by the computer of the area underneath the curve. But I know I can't have 1.5 hydrogen, so it must be doubled. It must be that this is a 2 to 2 to 3 to 2 to 3 ratio. And if I look at my splittings, it looks like I got doublets here, doublet here, singlet. This was blown up for me. It looks like a quartet, and this was blown up for me. It looks like a triplet. So I can see the multiplicity. I can see how many neighbors. We'll calculate that in a sec. And then lastly, the chemical shifts. The one on the right looks pretty alkane-like. The next one looks like it's attached to something with a double bond. And then I got something attached to something electronegative. And now I have stuff that's up here at between like 6.5 to 7.5. That's our aromatic region. I know that's an aromatic. That's something aromatic. So I've got a big structure right there. Let's start there, actually. So I've got this, right, which we said is aromatic. How do I know it's aromatic? That's because it shows up between 6.5 to 8.5. You know, somewhere in that region, that's going to be our aromatic region. That's smack dab in the middle of this. I also know that there are a total of 4 hydrogens on there. 2, and because I have one signal has 2 hydrogens, the other signal has another 2 hydrogens. It's just 2. So let's take a closer look at what this could be here, right? If I have 2 groups on the aromatic ring, right? Because again, I know I have 4 hydrogens. I can arrange them in like 3 different ways. I can have the 2 groups like this. I could have the 2 groups like this, or I could have the 2 groups, give myself a little more space, or I could have the 2 groups opposite one another, R1, R2, right? Those are my only options for how I could arrange those groups, right? 4 hydrogens on there, right? 1, 2, 3, 4 hydrogens, 4 hydrogens here, 4 hydrogens here. Now, if I take a look at these, only one of these can be a possibility. I know for a fact that these 2 R groups, I labeled them 1 and 2, they have to be different from each other. So I don't have any symmetry. So there's no symmetry here. They're different. They're unique. How do I know that they're different from each other? Well, I've already drawn an aromatic ring, which takes up 6 of my carbons. And I have 3 more carbons to put on here. There's no way I can draw 3 carbons on here and an oxygen and make it so that those 2 groups are the same as one another. There's going to be some asymmetry there. I know that I can't have R1 and R2 to be the same. So if I look at this first version here, right, I'm going to get 1, 2, 3, 4 different environments. 4 different environments, 4 different signals. I don't see 4 signals. I see 2 signals. So that one's out. Can't be that one. If I look at the next one, I see 1, 2, 3, 4 signals. Again, I don't see 4 signals. I only see 2 signals. This one's out. If I look at the last one, I see 1, 2 signals, which is, again, is what I see in my NMR. So this must be the shape. It must be, right? It must be that I have an aromatic ring with the hydrogens arranged like this, and then something is coming off at the top and the bottom like this. I don't know what yet, but I think that's what's going on with my aromatic ring. And again, I got all that information just from what was here, right? The fact that it's 2. Also, right, we'll take a closer look. These are doublets. That makes sense, right? These hydrogens should be doublets. They only have 1 neighbor. They should be doublets. So that all matches. Let's take a closer look at this signal, right? So I've got a 3H, right, which should be a 3 hydrogens. I see that it's a singlet, so there are no neighbors, but it's in this region here, right, between 3 and 4.5, between 3 and 4.5, that says that I should be on a carbon that is on an N or an O or an X. Again, in this compound, I only have oxygens. So that must mean that this is attached to an oxygen. Must be. So that 3H singlet at, 3.8 or so tells me that I have this chunk right up here. 3H, no neighbors, that's why it's a singlet, must be attached to an O. If I take a look at this next one, right, so we have the 2H peak. So I've got a 2H peak, I'll draw that one. So that's going to be this one. And just to clarify, right, this was the blue peak. If I look at the green one, it's a 2H. It's a quartet, so I think there's 3 neighbors. So I'm going to draw 3 neighbors to one side. And since it shows up between 3 and 1.5, I know that this is an H on a carbon that is then attached to a C that's double bonded to something. Again, I don't know if it's a double bond O or a C initially, but if I take a closer look at my molecule, I know I have an aromatic ring, and those have double bonds, right? Those have double bonds all over them. And since I only have 4 degrees of unsaturation, and a benzene ring has 4 degrees of unsaturation, I don't have any extra double bonds anywhere or anything like that. So it must be that this is coming off of my aromatic ring. So that's telling me that there's an ethyl coming off of my aromatic ring. That's what this green one is telling me. But now let's just double check. Let's look at our last one. I think I can already build this, but let's check our last one here. Our last one says we have a CH3 right? Because again, it's a 3H peak, and it's a triplet, which means it has two neighbors. So I'll draw two neighbors here in black. And it's between 1.5 and 0, so it's just alkane-like. Just pretty plain and boring, which that would be. And again, so now I think I have all of the pieces that I need here to draw my molecule, right? I think that these two ethyl pieces are the same, and that that's attached to an aromatic ring. And I have an O methyl group. That must be the other thing attached to the ring, right? So I think I have an oxygen here that's attached to a CH3. And I think that I have a CH2 here that's attached to a CH3. And that this must be my molecule, again, based on this NMR. So here are some examples of how we put together all the information, right? How many signals do we have? What are the integrations? What are the neighbors? What does the chemical shift tell us? So that we can support why we think that a certain structure is a structure, and how we can come up with a structure given some information. Now, not everything you'll be able to figure out given just an NMR. You'll need other things like carbon-13 NMR or mass spectroscopy or your IR. So you'll have to combine all of these so that you know what you have. And that's how science works. That's how we figure out brand new molecules that have never been made before, is doing this exactly. So I hope that those examples helped. Keep an eye out in the future for more information about carbon-13 and mass spectroscopy. In the meantime, happy studying.